Anyway, I started saying something about algebra. What would be in geometry, and I said something which is no, I did some kind of conception of affinization. And so, what is it? What I have in mind? But suppose we have some algebra. Yes, and the example can be the algebra of differential operators. On the line. So this is algebra which generates by generators P and Q. This is X. This is P over X. So the bracket is 1. Minus 1 is constant. And this differential operator X. Yes, and if we go to affinization, we want to do what? So here, the differential operator on the line. But affinization geometrically means that we are replace a line by infinite dimensional manifold currents from C1 to this line. This is infinite dimensional things, and affinization of this has to be the differential operator here. So this is infinite dimensional manifold, and so there are several ways to say what is the differential operator here, and naively or the way how it is doing in this business, we replace P and Q by some series. PT, UT, such that PT is the sign of I. I, U, the sound I minus I, and no, they're just components of the current. And these things we replace by a relation of the I UT is equal to I by J squared. So it no, it is no, because of some reason this correct definition, and this represents complete differential operators. So from the point of view of geometry, no, it is anything, but if we replace C by some manifold, which is more generic, then in principle, here we have an algebra differential operator, and yes, and we want to ask what is the differential operators. It is no, in general, it is not easy question. There are many approaches, but in principle, in many cases, we can create some kind of algebra. A little bit more precisely, we want the vertex operator algebra, which can get by this way. What is vertex operator algebra? It is not very important, but still we want to do something like that. Other type of example is short. That we have, suppose we have a big algebra G. Yes, and just the algebra. And if we go to affinization, it's where replace this algebra by current algebra. current on species, or maybe some version of G times universe. Laurent polynomials that have some function of C1, or we can, if I write this, mean that this is the algebra, but it is not for the field as it is, but for the bigger ring. Laurent, yes, and no, optimization, this is a commercial problem, how to do it. And people find that this is optimization, what we naively want, but really we get what is called G hat, and this is affine. That's Moody algebra. Well, and what no, in principle, this is affine algebra, and we also have performed the version. It is deformation and to a more complicated object, but in some sense, we also can see that this is affinization of G, or better to say, this is affinization of G. This is quantum group that has quantum group G, and this is quantum group corresponding to G. Now, there, idea of optimization is very fruitful and important because my time is restricted. Let me explain what really I mean. Let us take algebras. It is simple example, and here the base H and F. And if we go, no, this standard that shows the relation, this is Kaplan, and the H and H, and so on. If I go with SR2 current algebra, and this has to be SR2 times C universe. Yes, and it means that each E I have to replace by T, and component of this dt is I times minus I. Yes, and about the relations that I have. Now, let me draw some dots like this. So this is H0, no, because HT also like that we have E0, that F0, that we have 1, that 1, that is minus 1, that minus 1, and so on. No, this is base in the algebra. No, we have also central element, which let me know. Right, but relation nothing. So we have I, G, J is equal to H now plus G, and so on. And so it means that we have optimization of Cartan, we have optimization of roots generators, etc. Yes, and fine, but Next element, so the algebra, which I need is actually dq yes, and what is this? It is same, more or less same algebra, but we make up deformation. And let me not recall, not, but I will say something about it because I need some notations. Anyway, if we make up new deformation, what is happening? We still have generators 0, 1, 2, minus 1, minus 2, 1, 0, and so on. No, in principle, we have also something in Catan, so psi 0, psi 1, psi 2, psi minus 1, and so on. I do not want, so, and relation in SM2 are deforming. I do not want to write down all relations, but so before we make deformation of the icon and after deformation, the relation is deformation of activity, and usually we write it by the following way. That's T1. Let me recall that ET is just generating series. Here we write down T1 minus T equal minus minus yes, and it looks no, it really the deformation of the mutativity, and if you write it in components, you give us some sort of relation with that. Yes, and F Ft satisfies similar relations. Actually, they are the same, but we have to place two variables. Yes, and the relation to I Fj is psi I plus j, which is just the same, more or less the same as before. And the relation of psi is E are changing. It's really important, but let me skip it now. So it is a kind of deformation. Well, suppose so if we make the shift algebra, then we are doing before that this is no, I'll explain a little bit details about what is going on when I go to my real example. But what has changed? There's the two cases, and because no, it was when you see it first time, it was looking rather strange, but we are doing it before. That we can say that I Fj is 0 if I plus j less than some number. let me some numbers. So what is changing? So here, this bracket with this, no, plus something, and it is just SL2 like algebra. But now it is, if I take, for example, this and this, it will be also. But if you take some elements, say, the m is 0, f0, it gives us size. So relation of this and this are changing by such way that brackets are almost the same, but some brackets are 0, and but all other relations are not changing a lot. So no, this is a strange story, but let me explain, maybe saying more details, what is going on in mind. But first of all, what direction we are going. So before any shifting, so here we have some deformed algebra with Q usual one, and we can ask the question, what can be the meaning of affinization of this algebra? No, affinization is always going by the following way. So if we start from SL2 each area, then what we do? We take replace E by currents, and so ET, and for some of the I T minus I, and this EI just elements. So this is happening if we make affinization once. But in principle, if we like affinization, we can take this algebra and try to make affinization of it. So according to this naive story, it means that I have this EI and replacing it by the IT. So now affinization, it means that now we have collection of such current. Each current we get from this E and F, and it gives us something. And no, first of all, again, naively, if you look, you start from SN2, then you go to SN2 times T1, for example, and then you go to SN2 times T1 times T2, it is something like that. And so anyway, it is an interesting questions, but if the question, can we really do it? Can we create such an algebra which, first of all, we can apply to something and we can study. And if you ask, can we do after that something like that? Formally, yes, but nobody knows how to do it and for what reason. But in principle, it is also easy. Anyway, but if you really try to do it in this case, then the result is the result of this attempt, if you go by direction which I want to explain, is following. Now, first of all, it is better to work not with SL2, but because of some reason with J. So it means in J2 we have elements E, which H1 and H2, and F, where H1 and H2 are just such that. Here, for example, H1. Here with the H2 and again the F are here, and if we go from this to SL2 head, then it is like that. And in affinization, at least this part become commutative. Or more precisely, if we go to head, then such things the sample extension, it is not really commutative algebra, but some kind of Heisenberg, but it is not formal commutative algebra. And if you go the next step, then no, surely you can study the parallel of the algebra function on the torus. This is what I was describing, but real situation is more subtle, more easy. When we made up this second no, it is no like people when they do first quantization and then the second quantization, then it is very subtle. For Sterling, the similar is here. But first, what is happening? That now, so we have H1 I and H2 G, and if this algebra up to certain extension is commutative, but after affinization, we get here two algebra which I told you yesterday. This become one quarter of the and this become the other algebra. And it is clear maybe for some general principles and also from applications. So this object here in my example. So that result of optimization give me some algebra with the following structure. It is J1 plus J1 plus some represent some m plus m minus. So this is what we really get. So this is a graded object in degree 0. We have some mediocres, and we have additional generators. The m plus is representation of this, and minus is some kind of close. So this affinization is doing this, and this is in some sense in correspondence what I explained yesterday. Because let me recall what I explained yesterday. I said that if we have toroidal J2 double head. Then, no, this toroidal J2 double head, as I said, it appears as JM head over JNM minus 2 head. It means that we have embedded from J2 head here. Yes, and the algebra can be described or even defined by this way. So we, as I said, this parameter n can be even a complex value, and we consider here subalgebra we can meet with this. After that, we suppose the n to be a generic number, and this commutant gives us one possible construction of it. Yes, and also we found the principle saying us that we have J1 double head plus J1 double head and embedding J2 double head, and this is the extension. So this algebra from this point of view is an extension of this direct sum. So this is just what we have. But in this way, J2 double head is some quantum algebra, but it pretends to be something like J2 times C X inverse. Inverse, yes, and we deform it by some subtle way, but this is it. This is the algebra which I insist in. But anyway, that but such kind of construction from the point of view of this blackboard appear as affinization of such kind of scenes, and but it is usual current. But we can take shifted algebra and make up affinization, and this is just the algebra of what I need. And this algebra, depending in parameter A, which was in my surface, and this thing depending in this parameter A. Let me say a little bit more details. What is this about, and what we know about the extension? And, so a small new chapter is extension of vertex operator algebra. Why vertex operator algebra? Because, for example, J1 double head and understood as deformed vertex operator algebra, and if parameters Q1 to 1, we really get a vertex operator algebra. So, but if you are talking about vertex operator algebra, first of all, it looks more familiar. And second, we have more tools to deal with. And so let me go and now this part of my talk is for people who truly know something about vertex operator algebras, but there are statements which I need this for. So So we have vertex operator algebra is what the standard example. It can be the Sora algebra, it can be G-hat algebra, it can be something else. They are many of them. And it is one important element of a story. If you have vertex operator algebra, and by the way, the vertex operator algebra, which related to toroidal algebra, at least then, but goodness here mean the following, that we can, if we take good vertex operator algebra, then we have category of representation. And such category of representation have a structure which surely is calling structure of quasi tensor category. No, quasi tensor category, it means that on representation, in a good case, we can define something like tensor product. It's not honest tensor product, but it is almost. Because of that, it is quasi. But it is possible, again, in some case, to make not the usual, not quasi tensor category. And in very, very good case, this tensor category is a representation category of some quantum group. So this more or less means that it is a more of vertex operator algebra, and this is the model quantum group. And it all corresponds to tensor category. And it is a big correspondence. These two, they are surely not the same. If we have vertex operator algebra, in some cases we can find this. And if you have quantum group, in principle, there are many vertex operator algebra which correspond to it. So it is rather complicated on is a relation, but actually variables. And so no, there big trouble in this what I'm talking that for usual vertex operator algebra, this is important story, but in deformed vertex operator algebra, we do not know. Generally, but some it's unknown, but in vertex operator algebra, this is okay. Yes, and after that, how so this kind of relationship is used extensively, and one way is for that. Suppose I have vertex operator algebra, and suppose I want to make up some extension, even if it's not the vertex operator algebra is one, vertex operator algebra, and such kind of debating is also important. And personalization, for example, this is something like that. But if we look to this from the point of view of tensor category, it means that what does it mean? It means that we took is representation of degree one in some sense. From the point of view of quantum group, if you want to find this, and look what does it mean? It means that in that then category, you have to find some object in the R, which is calling the commutative ring of. So this object is something like commutative ring, but in a tensor category which is corresponding to R. And if you find this object and then find the corresponding representation of the vertex operator algebra V1, you can more or less easily find V2. Yes, and the example which I need is following. Suppose I have quantum group in Q of S2. Yes, and as I said, this quantum group is in charge of many versus operator algebra, for example, universal where Q is here is level, Q is exponent by I over 3 plus. Yes, it is such kind of exponent. If you have quantum group, no, if you have just usual algebra of G, then commutative ring object that it is some commutative algebra where G is X. And it can be function on G, for example, or something like that. If you are talking about quantum group, then the situation is similar. And actually, before you have to take quantum group as a general group, and you have to take function on this. No, because it is quantum group, so this is some kind of algebra, which is not complete. But it is possible to see that on this group we have the action of S2 from the right action, and you have the action of u actually Q minus 1 of S2 from the left. So such kind of product is acting here. And such things is vertex is commutative ring object for them. And this is again the standard thing from quantum groups and how to use it. So, well, for that we have corresponding universal developing with some key one. Here we have the universal developing for some level K2. And because here Q inverse, we need that 1 over 1 plus 2 plus 1 over Q2 plus is equal to some number. And it has to be integer, no better to say to have an even integer. This is a subtle story, but if so, again, we have quantum group, we have such object, and so we have two vertex operator algebra with some levels. Such levels determine this. If this condition is true, then we have the action of product here, and from the point of view of vertex operator algebra, it means that we can take the product of u as a 2 level P1 times u as a level P2, and this commutative ring object give us the extension of vertex operator algebra, and here we can construct the deep vertex operator algebra, which is extension. Yes, and actually, such kind of things is very, very important construction, and so what I said, that we need we have to as a two head and to be extended and get bigger out. And how such things work? Yes, my problem is restricted, but let me say some point where these stories work. I explain that we get, we have my geometric example. It is like this. And it is some number A here. So this line belongs to B. Yes, and this is my X. And what is going on? I'm saying that here some correspondences are acting in a zero of this. And here we have some kind of algebra which is actually the quotient of this, which is acting on equivariant P theory, and then we call it where parameter Q1 and Q2. And we have second quotient, which is unique here. Yes, and so here we have some parameters, and 1, 3 with Q1 inverse. You can check Q3 check. Yes, and actually here is U2 inverse, U3 inverse, but I have here Q1 power m, here Q1 minus m. So anyway, it is some relation between parameters on function. And I'm saying that from the point of view correspondence, that some things are acting here, some things are acting here, and the product is subalgebra of some big algebra of correspondence. And my statement is for.
So that's what is M? Is it related to air?
M and excuse me, it is more or less
air.
Yes. Maybe some shift which I need, but it is more or less. Yes. So this product is subalgebra inside some beings, which I said this is more correspondence. So this here, some others along this line. And if parameters Q1, Q2, Q3 go to 1, then what is living here in geometric examples, if you are talking about Gilbert scheme, or you are talking about physical scheme, or some examples people like that. Such limit gives you two vertex operator algebra. One vertex operator algebra that is given here. Second vertex operator algebra that is given, and all it is all such kind of extension. No, because this is extension, then of product of two vertex operator algebra, we can see that actually we are living in this. So it means that now it's vertex operator algebra, this extends here, this extends here. So we have this ring object, and this ring object determines the extension, and this is just the extension which we have in such situation. I want to say a little bit more that if we are no, this I explained version 2, but here such algebra which is here are more complicated, but phenomena is just the same. So here I'm saying that if we want to make up the extension of the product by this way, you need a relation that 1 plus 2 plus 1 and 2 plus 2 has to be equal some integer. And if it is this, then the product of corresponding q is 1, and so we are living in our side of my story. Yes, and so it means that all this dependent in this M. And if you look to this part of the story, then this M is actually A. So why is other question, but at least there is some bridge between these two things. No, in particular, it means that from the point of view of geometry, we can construct some algebra which is acting here, and after that, we make up limit 1 to 1, and in the limit, we find some vertex operator algebra. And so representation of this vertex operator algebra is in charge of geometry, which relate to this kind of spaces. For example, different story, the characteristic of sheaves and the other. No, the category of concurrent sheaves. Such kind of Gilbert scheme, they can be maybe can construct it through the representation of this vertex operator algebra. Maybe it is too much, but something like that. So this is my story, but well, I need to say more things. And now let us return to my real case. My real case, I have J1 double head, J1 double head, and I want to make up the extension. Extension how? That J1 double head, this is the formation, as I said, the algebra of different space. Yeah. And such algebra has a representation in the space of CF. And let us call this representation from equality union model representation. And let us know why. get one because it was according to this. So if I have such product, then this algebra has a classification of one that is the one in the representation of this is the representation of this. No, I didn't mention, but for after quantum deformation, also such representation is also for the dual one. And here it is M1 star times yes, and so these things by model, so it was modeled over this. This is also modeled over, and their construction, their extension actually is doing by this way. So we have this. We add such kind of product and also do things, and then we can make up the algebra which generated this generator, and it satisfies some limit. And I want to finish either whole step, and again, from the point of view of geometry, such kind elements from here, in the some other sort of correspondences, we change the shift along this line. No, it is not easy things, but still, I want such kind of structure of algebra. We can see it. But let me say what condition where we have this kind of shifted fine algebra, toroidal algebra. For that, let us say the following: that F1 is something like this. So let us say that some fx is generating function. So f2 star are something like this. And if the generating function of this are element of fx, and so we can see that we have these two things, and we extend it by some kind of operator with dependent on x and y. Here also x and y. Yes, and after that, if we so now what we tried to do is Nietzsche Trimper and moving, we try to make up as explicit as possible. So it means that it is possible to find out some representation of algebra. That this is some explicit. And so in a corresponding algebra, so we have two J1 down, and also we have generators in I, maybe C, C, and F, E. So such kind of things is nothing as I use X in the X here, but this is a term of X times the star X times Q. However, depends on notation, but it is one. Yes, and similar story. So also product to such things which I, and if you look what is this, then the situation depends on M, or no, maybe A. No, because this is algebra depending in A, and the question is where is A here? Now, first of all, A is in parameters of this two one toroidal algebra. It is also in relation of the I itself, but similarity with the twisted algebra is formed. If we take M, it is shifting parameter, then and starting to calculate the I F and F3 from here and from here. Then, if M is positive, C equal to 0, I minus F3 is less than yes, I think it's correct. Yes, and if we consider boundary case, then we have then it proves to this theorem of toroidal algebra, and the generators here appear as such kind of break. If you take f of minus m plus 1, then you get more generators from here. So structure is just shifting. So you have my story mean that operators psi I, which they replacing by these things, and this become again. I have my generators high independently. Using this approach, they become these processes. So, no, rather than use calculation saying that such kind of structure really appear. Yes. No, I think that this is an interesting point that this is some more or less relative new algebraic object which deserve this time. Yes. And so again, it is more or less clear why I call it affinization of shift. Yangian, because it is just not Yangian, but an algebra that I become currents and the relations are relations, which should be much more complicated than of toroidal case, but big similarity. Okay, no. So thank you, just trying to solve.
Questions?
Just maybe it would be easier to see. So is similar thing happening in less affine case. So if you start, like you explained us initially that you can construct this with SO2, just affine SO2. So when we also do it from like two diagonal pieces, then we probably will have only one more, like this Q1 to the power of 0, and somehow extending to Heisenberg's to more Heisenberg.
No, it is possible. Something is here.
And is there also number n? Like
no, M is shifting.
yeah, but can you construct also shifted SO in the same way, but like once affine J2, sorry.
Shifted J2.
Yeah, affine J once affine, not the right just affine.
No, you mean geometrically or how?
Just in similar procedure, algebraic. Okay.
Algebraically, yes. Geometrically, we know.
So here this M is just the degree of the line bound. right?
Yes,
So it's and delete at the same time.
the same some
Integer correct.
no, some details I should not explain, and you know that they're shifting into different sides and so on. And all this story also depends what positive, negative. In this case, shift different ways. No, it means that at sign of M is different. Here, if you start a calculation, you have
So M can be negative, right?
it can be negative. So you start with zero. If zero is F0, you can start if it is positive, then it is zero. But if it is negative, then this bracket is some generated from here. Not you have not zeros, but it is like no. In this case, it is like E0 and F0, depending in M is some element from here, which depends on M, sure. If M is big or smaller, I get confused, but such kind of bracket can be more. And if you take after that E1 and F0, it will surely be more. So you have no zeros. No, same story happening. Same thing.
Similar story, you mean that in the less affine case, so when we have one pattern, then the central part becomes commutative. So it's just the usual
Yes, and what to say, that it is also open for me. This question, but no, people who worked with this shift business from maybe when they started from the branches and so on, then they should formally they should try to go to parallel algebras and therefore is and it is not still no, it has to be related, but formally it is different. So anyway, it is some kind of new things, each calculation and each statement gives you new question to think about. So it is a rather complicated structure right now.
You mentioned in your title in both of the lectures applications to integrable systems, but I didn't hear anything about integrable systems.
You are right, but this is my fault, first of all. And second, if I will have third lecture, I'm sure I can say something, but not now.
So you will discuss that tomorrow?
No. Tomorrow it will be colloquium. If people come and I will talk by this way, this for colloquium it is very bad style. So maybe I can do it better, but at least I have to explain more things.
I guess I should mention that after your talk tomorrow at 3:30, there's another colloquium in which Alex Maloney, who was awarded the CAP CRM Prize for Mathematical Physics, will be giving a talk about quantum field theory and various applications. And that will be on the 6th floor if anyone's interested in attending. It will be 1/2 hour after your talk.
No, thank you. I think I will come, but can be interested.
Yeah, maybe one more question. So you mentioned that that there are quantum groups responsible for the categories.
Yes.
Of writing algebras, and what do they look like in this case? So when we take conformal limit,
take some quotient of these and things. So it means that, in principle, in general, in the limit some kind of infinity, quantum in charge of them. But the work with training infinity is very complicated. Therefore, we are looking at this quotient for JVM.
And the same depends on
No, I think it's a choose of representation. So, from the point of view of geometry, it is a one sheet. From the point of view of this, is what representation you category take. Yes, and so to be honest, I mentioned it, but if you want to apply this idea with tensor category, first, you definitely have to go to control limit. But second, you need to consider some quotient where corresponding tensor category related to finite dimensional quantum group. In this case, such kind of theorem, this can be applied. If it is dimensional, if it is also true in some sense, but no, it is rather hard to make up some kind of like experiment. Theoretically, it is possible to do, but to be honest, I do not know how.
You mentioned the Coulomb branches minutes ago. So do you think this toroidal algebras, the toroidal algebras related to Coulomb branch or the affine river?
This I do not know, but this for long branch how it is working. So you have this shift of Yankian functions of the long branch are quotient. So it means that if you want to take this long branch and take affinization, if you go many loops there, and you want to apply all this theory to that. In this case, I think you need this. I'm talking about I cannot accomplish. I just think so.
So the loops to the Coulomb branch.
Yes. Affinization is affinization. All objects which we have, we can affinize them. Why not? If we have Coulomb branch, if we are talking about quantum technology, for example, then we need. Or we can take this affinization loops and taking cathedral shifts there, trying to say something about this. Now, in principle, by this way, we can is it go enough or not? I don't know, but in principle, we take affinization, some kind of case theory for that. Then we are interacting to that. I mean, it's a national question. Anyway, if you take loops, then equivalent parameters have one more on the loop. Therefore, what is acting depending on parameters. Yes. People usually expect that we make something like that, and after that make up an elliptic information. So this is a national expectation, but maybe correctly